There are 5 subtopics which we will be covering under this topic, matrix algebra. In this video, we are going to cover first 2 topics. A matrix is defined as a rectangular array or a table of numbers, symbols or expressions arranged in rows and columns. A matrix is always bounded by brackets and labeled by a capital letter. There are certain terms which are used in matrix algebra. Let us look at them one by one. Elements of a matrix. Matrix is made up of rows and columns. Each number in the matrix is referred to as an element. These elements can take any value from integers to real numbers. They can be positive, negative, or even fractions. Order of a matrix or dimension of a matrix. An order or dimension of a matrix is given by the total number of rows and total number of columns. Each matrix has a fixed order or dimension. Number of rows are given by n and number of columns by the letter m. An order is written as n by m at the right hand bottom corner of the matrix. Principal diagonal. The diagonal which can be defined only for the square matrix and which runs from the left hand top corner to the right hand bottom corner of a matrix is referred to as principal diagonal. All the elements on the principal diagonal are referred to as principal diagonal elements, and all those which are not on the principal diagonal are referred to as non-principal diagonal element. A row vector. When a vector is made up of a single row and multiple columns, then that is referred to as row vector. A column vector. When a matrix is made up of a single column and multiple rows, then it is called as column vector. A square matrix. A matrix with equal number of rows and columns is called as a square matrix. Principal diagonal can only be identified for such kind of matrices. So a 3 by 3 matrix, 2 by 2 matrix, 4 by 4 matrix where n is always equal to m are referred to as a square matrix. On the other hand, when a matrix has unequal number of rows and columns, it is called as rectangular matrix. Like say for example this matrix, it is not having the number of rows equal to number of columns. The number of rows are 3, number of columns are 2. So it is called as a rectangular matrix. Principal diagonal cannot be defined in case of rectangular matrices. There are certain types of matrices or family of matrices. Null matrix or zero matrix. A matrix of any order having all the elements equal to 0 is referred to as a null matrix or zero matrix. The second one is identity matrix or unit matrix. A square matrix wherein the elements on the principal diagonal are equal to unity, that is equal to 1, and the non-principal diagonals are equal to 0 is basically referred to as identity matrix or unit matrix. The J matrix, a matrix of any order having all the elements equal to unity, that is equal to 1, which is not necessarily a square matrix, is referred to as a J matrix. Diagonal matrix. All the elements which are not on the principal diagonal are equal to 0, while all the elements on the principal diagonal may take any value other than 0. So it can take the value of 1 or anything higher than 1. Thus, identity matrix is also a diagonal matrix, but the reverse is not true. Triangular matrix. No specific alphabet is reserved for this. Triangular matrix is defined on the basis of elements, values, and their position. The first one is referred to as upper triangular matrix. The triangle above the principal diagonal, has got non-zero values, and even the principal diagonal has got non-zero values, but the elements below the principal diagonal will be always equal to 0. That is upper triangular matrix. Exactly the reverse thing will be there in case of lower triangular matrix. You will find that the principal diagonal and the non-principal diagonal that lies below the principal diagonal, all these elements are not equal to 0 or greater than 0, while the values which lie above the principal diagonal, they will be always equal to 0. That is lower triangular matrix. Next is a permutation matrix. Every row and every column has a single value of 1 and two values of 0. So the value of 1 over here does not necessarily lie on the principal diagonal. It may or it may not. Symmetric matrix. It has to be a square matrix, and this matrix is symmetric about the main diagonal. So you can see that on the main diagonal the values can be 0 or 1, but the non-diagonal values are exactly mirroring themselves, and that is why it is called as symmetric matrix. Now we come to the next part, that is determinant of a matrix. A determinant is a scalar value that is a function of the entries of a square matrix. It allows characterizing some properties of the matrix and the linear map represented by the matrix. It is a quantity obtained by the addition of products of the elements of a square matrix according to a particular given rule. The determinant can be viewed as a function whose input is a square matrix and whose output is a single number. So in order to obtain a determinant of a matrix, the matrix has to be a square matrix. Let us look at this. In order to obtain a determinant, what we will have to do. Now let's say, for example, a determinant of a matrix, it is always represented in this particular manner. The name or the alphabet which that particular matrix represent, it is always put in these two standing lines or the modulus sign, but these are not the signs of the modulus, but these are simply the standing two lines which are drawn outside that alphabet, which simply means that this is called, rather it is being called as a determinant of A. Now, if the given matrix is of an order of 1 by 1, then the determinant of such a matrix is that element itself. For example, I have a matrix A which is having a single value as its element over there in that matrix. So the order of the matrix is 1 by 1. The value is 21. Now what will be the determinant of A? It will be that particular element itself, that is 21. So it is very simple. If we have 1 by 1 matrix, then the determinant will be that particular element itself. Now we go to a slightly higher order, that is 2 by 2. Now in case of 2 by 2, if we want to find out the determinant, it is computed by product of positive diagonal, that is referred to as PPD, product of positive diagonal, minus the product of negative diagonal. And it is being given in this particular formula as determinant of A is equal to product of positive diagonal minus product of negative diagonal. Let us take an example and solve it. We have this matrix A and we are having these 4 elements. So it is 2 by 2 matrix. It is a square matrix. We can find out the determinant for that. How do we go about? As I said, the first part is product of positive diagonal. So we have to identify the positive diagonal and the negative diagonal. We know the positive diagonal will always run from left hand top corner to the right hand bottom corner. So this is your positive diagonal. The other diagonal will naturally become the negative diagonal. So product of positive diagonal, so it will be A into D. That is what is written over here. Minus the product of negative diagonal, that is B into C. This will give us the value for determinant of A. Now let us take actual values and try to find out the determinant for 2 by 2 matrix. We have this particular matrix with the values 2, 3, 1 and 4. First part is product of positive diagonal. So this is your positive diagonal. There are two values which you have to multiply. 2 into 4, here we have written them, minus 3 into 1. So it gives us 4 2s, that will be 8 minus 3. So the final value is 5, and thus the determinant of this matrix A is equal to 5. Now this was okay when we are having only a very small 2 by 2 order matrix. What happens if the order of the matrix increases from 2 by 2 to 3 by 3? In that case, we will be following the same rule, which is referred to as Cramer's rule 1, but slightly modifying as per Cramer's rule 1. Now, if the given matrix is of an order 3 by 3, then the determinant of such a matrix is computed as summation of product of positive diagonal minus the summation of product of negative diagonal. Always remember, you will have to identify the positive diagonals and you will also have to identify the negative diagonals. So this is the example. This is the matrix A which is given to us. Now what is the first step that we will see? The first step is copy and rewrite the first two columns outside the matrix. So this is your original matrix A. What I did is that this is my first column and this is my second column. I have simply repeated those values outside the column. This is my first step. In the second step, we will be identifying the positive diagonals and we will be taking the product of each positive diagonal and then take their sums. So this is summation of product of positive diagonals. Let us identify the positive diagonals. Now this thing we have rewritten over here. This is your first principal diagonal. This is the second one. This is the third one. So you are having three principal diagonals. We will be taking the product of each of the principal diagonal over here. So it is 2 into 6 into 8 written over here plus 3 into 7 into 1 plus 4 into 5 into 0. This gives me an answer of 117. Next step is to identify the negative diagonals and then take the products of each of the negative diagonal and then finally sum them up. So these are now my three negative diagonals. I'll be taking the product of them 4 into 6 plus 1 plus 2 into 7 into 0 plus 3 into 5 into 8. And all this summation of product of negative diagonal, the value gives is 144. Now we sum up both of them. Look at the summation of product of positive diagonal minus the summation of product of negative diagonal. So it is 117 minus 144. So finally your answer from the determinant of A is equal to minus 27. So by using Cramer's rule 1, we have found out the determinant of A over here. Thank you.